Shaw, who will be telling us about his career in superconducting detectors and how he builds them for JPL and designs them. So take it away.
Okay, thanks a lot. Well, thank you very much for the engineering club for inviting me to come and chat with you folks. Can you hear me okay, or is it better?
There's an on switch on the blue one.
Is it better with the microphone? Or better without the microphone? What do you think? Without the microphone? Yeah, it's a little more informal, right? Okay, so I'm not Shaw. I'm going to be telling you about...
It's going to fall.
Oh. Exactly. So just a quick word about myself. Oh, okay. There must be a little slope to it. Thank you very much. It's, yeah, I feel like my security detail. Dive in and, yeah. So I was born and raised in Fairbanks, Alaska, which is very different from LA. Very beautiful, but you know, we had lots of cold in the winter and lots of sunlight in the summertime. I do have an 8th grader here at Macchiato High School and also a 4th grader at LCE. I am a mentor here for the engineering club, so that's part of my entree to this event tonight. I have a PhD in physics, and I'm the supervisor of the Superconducting and Quantum Devices group at JPL. And not to worry, I'll tell you what superconducting detectors are. I also have a visiting research appointment and a lab on campus where we can work with students, PhD students, and such at Caltech. And so I've been leading the development of a particular kind of detector that I'll tell you about called a superconducting nanowire single photon detector for about 10 years, since 2012. My wife is a public defender, which is a very different but also very important job. If you're curious about that, I can tell you about that later. And just a few words about JPL. If you don't know, it's right next door, even closer than McDonald's. So JPL is a research lab run by Caltech for NASA. It's the nation's leading center for robotic exploration of the solar system. So we design, build, operate unmanned spacecraft for scientific applications, things like Earth-observing satellites, instruments for space telescopes, stuff like that. We also perform technology development and R&D. And so technology development is really what I do, and that's what I'll be telling you about today, as I have really just a few slides and then some discussions about the science career path and the physics career path, in case you folks are interested. And then we can leave plenty of time at the end for conversations and chat as well. So some of the key science areas that JPL is interested in are astronomy, earth science, and planetary science, really trying to answer big fundamental questions about, you know, where life came from on Earth, whether or not there's life on planets outside the solar system, etc. And the other thing JPL does is operate the Deep Space Network for NASA, which is a radio communication network that communicates with all spacecraft outside of Earth orbit. So we have big radio telescopes in the desert all over the planet. So there's about 7,000 employees at JPL, plus students and contractors. And so when you get into college, you might, if you're considering careers in science and engineering, you might keep JPL in mind for internship opportunities in the summer and stuff like that. Okay, so I just wanted to very briefly explain what superconductivity is, because it doesn't necessarily come up every day in conversation. So superconductivity is a miraculous property that some metals have, where the electrical resistance of a piece of metal drops suddenly to 0 when you reach a certain temperature. This is a consequence of quantum mechanics, which is the branch of physics that describes really small things and systems that have very small amounts of energy. And it's a phase transition, just like, you know, water freezing into ice is a phase transition, right? So the way superconductivity works, is there a pointer?
We do not.
Question? No pointer? Okay. Oh, maybe I can point with this thing. Oh yeah, I can point with this thing. So just to briefly explain what stuff is made out of and what resistance is, you know, if you apply many of you folks are familiar with circuits? Raise your hand if you have some experience with circuits. Okay, just about all of you. So you know that when you apply a voltage to a piece of metal, like a wire, some current flows through the wire, right? And the amount of current that flows when you apply some voltage is the resistance. V equals I times R. And the resistance is sort of what's holding back the amount of current that's flowing, right? What's happening actually inside the metal is, of course, made up of a lattice of atoms that are locked together like little ping pong balls. And there are electrons that are flying back and forth through the lattice of atoms. So generally speaking, in a metal, all the electron shells kind of overlap with one another, and electrons can just fly right down past the lattice in a nice conducting piece of metal. However, the electrons can collide with each other, or they can bounce off of the atoms in the lattice. And when that happens, the electrons that are flying around, they lose energy, and they get kind of slowed down. They have to stop and speed back up again. And the amount of current that actually can flow is limited by that bouncing around. Now, it turns out that in certain kinds of metals, including really common metals like aluminum or lead, or more exotic kinds of metals like niobium, there's this magical property called superconductivity, where below a certain temperature, the current is no longer carried by electrons, but by pairs of electrons. So the electrons always want to bind together into pairs. And those pairs, if one of them is spinning clockwise, the other one has to be spinning counterclockwise. And if one of them is going to the left, the other one has to be going to the right. So they're locked together in conserving, each pair conserves the energy and momentum that the individual electron might have. So what that means is if you bump into just one, it won't affect the pair. In order to affect the pair, you would have to have the one on the left bump into something and change its momentum in just the right way so the one on the right changes to compensate. And that basically never happens. And so as a result, even though the electrons are still bouncing around in the material, you never actually feel any resistance. So it's not that the electrons stop colliding. The electrons are still colliding, but it's because in the superconductor, the current is carried by these pairs that are bound together. It makes them kind of isolated against the electrical resistance. And the electrical resistance just falls straight to zero. And that has some kind of crazy consequences. That means if you put some current in a little loop and you set it going, it'll spin around in that loop forever, like literally forever. People have done experiments where they put current in a loop and they come back a year later and the same amount of current is in the loop. It literally, there's nowhere it can go. So you might ask yourself how you could use this phenomenon to make useful devices. So there's really three kinds of devices. There's other things people use it for, but there's three main kinds of devices that we are interested in that are kind of very high technology devices where you can exploit this principle of superconductivity to do entertaining things. One is to make sensors. You can exploit the fact that that phase transition is really sudden to make a sensor which is really, really sensitive to very low energy light, very, very faint light, or light where every photon barely has any energy. So that's a big part of what we do in our group at JPL, are developing state-of-the-art sensors that are super, super low noise and really wonderful properties and are exquisitely sensitive. Another thing people do with superconductivity is to make circuits for quantum computing. Anyone know what quantum computing is? Okay, no worries, no worries. It's a weird thing. Quantum computing is a way, so quantum mechanics is a branch of physics that describes individual things like single atoms, single electrons, single photons, all obey these strange laws of quantum mechanics where the rules of statistics by which particles move around are actually somewhat different from the way they move in the everyday world. And because of this difference in the way the laws of statistics play out for quantum systems, if you encode a bit of data in a quantum system, then you can do operations on that bit of data that you could never do in a classical computer. And so there are certain things where a quantum computer might be fundamentally faster at, than a classical computer for certain kinds of operations. One good example is that for a classical computer, it's really fast to multiply numbers together, but it's really slow to factorize numbers apart. So this is like sort of infamous for a computer. And this is actually a principle on which a lot of cryptography relies. So you may be familiar with having a cryptography protocol on your web browser that says it has a 512-bit key or something like that. And that's because for a classical computer, it takes forever, years and years, to factor a 512-bit number. But it only takes like microseconds to multiply two numbers that are 512 bits. It's just that there's no really good, fast way to factor numbers on a classical computer. On a quantum computer, that's actually not true. You can factor numbers basically at the same speed that you can multiply them together. And so there are things like that that are problems that are fundamentally known to be really, really hard for classical computers that you could do very quickly if you had a quantum computer. The problem is that quantum computers are extraordinarily cantankerous to build because you have to have quantum systems like atoms and control a single atom what it's doing, which is hard. You need like a bunch of lasers or something like that. Using a superconducting circuit, you can make sort of an artificial atom. You can make a circuit that obeys all the same laws of physics that the atom behaves, and then you can keep track of what that atom does. And now it's something that you can stamp out on a chip. And so the quantum computer is another application of superconducting devices. This is because the basically when you have these pairs of electrons, you are operating in this this real quantum state that enables these quantum computers. Also, because you have circuits that don't dissipate any heat because there's no electrical resistance, you can make super, super low power digital electronics. So this is the third thing that people sometimes do with to apply superconductivity in your everyday life. Well, yeah, here's my everyday life. So anyway, they can be used for sensors, quantum computers, and electronics. The trick, of course, is that superconductivity happens, as I mentioned, below a certain critical temperature. That temperature, depending on the material, may be only a couple of degrees above absolute zero, or in some cases even a small fraction of a degree above absolute zero. So these quantum computers, for example, typically operate in a machine that has to cool them down to about 1/100th of a degree above absolute zero. And so you have to have these cantankerous refrigerators and machines in order to keep all of this stuff cold. But that's also part of the fun. So if you really want to make these devices work well, you have to have the infrastructure to get them cold. So these are some areas. So at JPL, we mainly focus on the sensors, and we work on a variety of different kinds of superconducting sensors, each one of which exploits superconductivity in a slightly different way. And some of the science areas that this technology supports, there's the three kind of classic areas and realms for superconducting detectors are astronomy. So in our group at JPL, we recently proposed a far-infrared space telescope that will look at infrared wavelengths beyond what James Webb can see. James Webb can see out to 28 microns in the infrared. This telescope would go from 25 to 240 microns in the infrared. So if you folks probably know about astronomy, when you look further out into the infrared, you actually can look further back in time because basically the universe is expanding, and as galaxies and other things are flying away from us, they get Doppler shifted out to the red, and they start to look redder and redder as they go farther and farther back. So if you look at really, really old light from when the universe was just being created, or early light, it looks more and more red. So being able to look out into the infrared allows you to peer further backward in time. And so some of these things, so this telescope concept, which is called PRIMA, which would fly these superconducting detectors operating at 1/10 of a degree above absolute zero, would be able to look at the processes by which galaxies are formed and study the physics of galaxy formation. Superconducting detectors are often used for cosmology, studying the basic physics of how the Big Bang happened. And some folks in our group at JPL have been working on a long-standing project to make these superconducting detectors, which are extremely sensitive detectors for microwave radiation, millimeter wave radiation, which is called the cosmic microwave background, which is the original light left over from the Big Bang. After the Big Bang, there was this period where the universe grew really, really fast. Some people think even faster than light itself. And there was sort of a big flash of light about 400 million years after the Big Bang. And that light is still observable today, if you look at it. And by studying very faint discrepancies of how that light is distributed across the sky, you can actually learn about the physics of what happened in that period in this very early history of the universe, when all this very strange physics was going on. And so, superconducting detectors are really key to understanding that kind of cosmology. So we actually work with a group at Caltech that we fabricate these detectors, and then they put them in these, sub-Kelvin cryostats, and actually deploy them at the only place in the world which is dry enough and at high enough altitude to be able to see at these very long infrared wavelengths, which is the South Pole. And so they take every year these detectors to the South Pole, and they build up this instrumentation. Another area that superconducting detectors are useful for astronomy is in exoplanet detection. So people are very eager to understand whether or not there's life on other planets outside the solar system. There's so many planets out there. You figure some of them must have life, right? And it's hard to think of a more burning question than that. Because superconducting detectors can be incredibly low noise, they can be used to look at very faint light coming from a planet outside the solar system and try to infer what the spectrum of that light is, to find out if there's oxygen in the atmosphere of that planet, or other signs of life in the atmosphere of that planet. So these are all applications in astronomy where superconducting detectors are really important. Another application is, as I mentioned before, quantum information science. That's things related to quantum computing, but also what's called quantum communication, and doing fundamental tests of quantum physics. So we work with a lot of people in that community. And then there's another area which I'll talk about more in a moment, dark matter detection, which is really entertaining. And then they can be used for other things too, biomedical imaging, laser communication, remote sensing, etc. So now I'm going to zoom in, having given you the broad outline. And if anybody has any questions, you can holler them out, or we can wait till the end. But no worries. So now I'm going to zoom in on a particular sensor technology that exploits superconductivity, so you can sort of see how we use this in practice. And this is the detector technology that I've been working on personally at JPL for some time now, called the superconducting nanowire single photon detector. Now this device is basically a narrow, skinny little superconducting wire, which is meandered to fill up some active area on a substrate, on a chip. When you flow current through this wire, the heat from an individual photon is enough to warm up that wire, enough so that it switches over that transition, and it goes from being in the superconducting state into this resistive state. Now this wire is super small. It's only like 3 nanometers thick. And so if you make that wire really small, then that resistance becomes really huge. It's like a kiloohm of resistance. So when that happens, it's like a switch that opens up. If you folks are familiar with circuits, you have a current flowing through your wire, and then when the photon, normally it's just happily flowing through this wire because the resistance is 0. And then when the photon comes in, it's like a little switch that pops open in a matter of picoseconds, and the current that's flowing through doesn't want to flow through your wire anymore. If you hook up a little amplifier in parallel, it'll want to flow through that amplifier instead, and you get a really nice little spike out. And that spike, you can look at and see exactly when the photon arrived, and you can have a little time tag. It just clicks every single time a photon arrives, and it can tell you to an accuracy within a few picoseconds, how a few trillionths of a second, how exactly what time that photon arrived. And it turns out that that's useful for all different kinds of science. And the other thing to know about this detector unlike almost any other kind of detector, is that it is a real fundamentally digital detector. It gives you a signal every moment that the detector comes in. You don't have to, wait around. These are some of the people that work on this technology. So as you can see, they all mostly look pretty happy. There's a number of JPL staff researchers who are working on this at least some fraction of their time, mostly in our group at JPL. And then we have postdocs and grad students. I'll talk a little bit about how the sort of career path in science works toward the end. But then we also work with a number of different colleagues at other institutions, at other universities and other national labs, kind of like JPL, to both on developing the technology itself. So we have partners that help us where we all kind of work together to make the technology better and better. And then we also have folks that are using the detectors in different kinds of science experiments. So we work with people who work in these different fields that I talked about: astronomy, dark matter, other areas, quantum information science. So just to put a face behind it, don't worry too much about the details. This just shows you sort of the kinds of things that you care about when you have a photon detector. If you're detecting an individual photon, you might want to detect every single photon. This detector can detect 98% of the photons that comes in. That's actually pretty unusual. So it's really, really good at being able to tell every single photon that comes in. The detector has really low dark counts, so it almost never fires when a photon wasn't there. It actually only fires about once per day if no photon arrives, and that's really, really unusual. So the fact that the detector almost really never fires unless a photon came in, that's really the thing that makes it so useful for things like astronomy and dark matter detection, where you want to look at really, really rare events. That's why you care about having these low dark counts. We also have been trying to make the detectors work over a really wide range of different wavelengths, not just visible light, but also in the infrared, all the way out to 30 microns, which is a really long wavelength, and deep into the ultraviolet, so we can look at funny parts of the spectrum where there's no other detectors that work. We've been able to time tag photons to a few trillionths of a second. We've recently been working with our colleagues at NIST in Colorado to make cameras of these detectors, so we can do time-resolved imaging for all kinds of biomedical applications and other kinds of things. So we can basically have a camera where the movie on your camera consists of individual photon arrival events. And we've made detectors that can count with this very high time resolution at billions of events per second. And those are these sort of peacock-shaped detectors that we got down here. So I just wanted to briefly mention a couple of applications that involve this sort of technology, just to kind of give you a little flavor of how these detectors are used now that I have told you what they are. And so one of the things that we've been doing a lot at JPL is using them for laser communication. So here on Earth, we take it for granted all the time that we have laser communication in all the fiber optic networks. And you folks are all teenagers, you can watch YouTube, wherever you go. And that's because we have fiber optic cables everywhere that are exploiting the super high bandwidth of light to be able to get tons and tons of information in and out of Google's data centers, right? For spacecraft, we're still stuck in the kind of stuck in the 50s with radio waves, right? Where you can't send a fiber optic cable spooling out after you're onto your Mars rover. You're really stuck with a little radio transmitter that hasn't changed that much in the last 50 years. And we have these giant radio dishes out in the desert, some of them as big as 70 meters, that receive these really faint radio signals. And so some of these radio signals are only kilobits per second. It really limits the kind of mission that you can design if your communication system can only send a really narrow pipe of data back. So it's a big priority for NASA to be able to send more data back from spacecraft in deep space. People want to make things that will look for life on outer planets and in the solar system and things like that. We want to send back high resolution video. Maybe there'll be astronauts on Mars and they'll need to see the Super Bowl. You know, you have to be able to send more data back from spacecraft in deep space. So it turns out that you can do the same kind of optical comm that we do here on Earth, but there's a lot of complicating factors, it turns out. You have to have a spacecraft with a telescope that's really stable. You have to have really sensitive detectors on the ground. And so the longest range demonstration of laser communication that's ever been done, until a couple of weeks ago, was the lunar laser communication demonstration, which was done from the moon back in 2013, which was led by MIT Lincoln Labs and Goddard Space Flight Center, but we were also involved. The moon is, of course, 400,000 kilometers away. Now we are trying a very ambitious project called DSOC, the Deep Space Optical Communication Project, which will actually, for the very first time, try this laser communication from interplanetary space. So this is so at JPL, we built a laser transmitter, which is gone on a spacecraft called Psyche, which actually launched on October 13th. It sends data back. It's designed to send data back from a range. The spacecraft is going out to the asteroid belt, so past Mars. It's designed to send data back at distances as far as 400 million kilometers. Now the moon is 400,000 kilometers. This thing will work out to 400 million kilometers, so it's 1,000 times farther. And the amount of light that you get back falls off as 1 over the distance squared, because it's like the surface of a sphere getting bigger, right? And so that means it's actually 1,000,000 times harder than any other laser comm demo that's ever been done. And it's not very often that people want to go up by a factor of 1,000, right? I mean, the first robot competition usually doesn't make a competition that's 1,000 times harder than last year's, right? I mean, maybe it's twice as hard, but probably not 1,000 times harder. And so there were a lot of new technologies that went into DSOC on the spacecraft and on the ground. We built a very fancy superconducting detector array using the superconducting nanowire sensors that I just showed you, because when you have a blinking light on the spacecraft and it hits the ground, you know, from 400 million kilometers, the size of that laser spot is actually about 1,000 kilometers in diameter. So even using a very big telescope, you know, you're just sticking a tiny little pinhole in that beam that's the size of the western United States. And so you're very deep in this single photon limit. You only get like 1 photon at a time coming back from the spacecraft. So you need exactly what our detector does. It's something you need to count single photons of light. Actually, I didn't even say what a photon is. Does everybody actually know what a photon is? Anyone? A photon is an individual particle of light. If you turn down a beam of light, it gets dimmer and dimmer and dimmer. But when you start to go beyond a certain point, you'll find that the light is no longer coming as a continuous wave. It just comes in individual little raindrops almost of light. The light actually has this particle component, which is a feature of quantum mechanics. Each one of those particles of light is called a photon. So with this detector, we're counting individual photons, and that's the regime that we're in to communicate with the spacecraft. So we're very excited about this. We've worked on it for years and years, and it's just now been launched. So we just closed the first links, actually a couple of weeks ago. So we built a ground terminal where we have our fancy superconducting detector sitting in its 1 Kelvin cryostat. So it's about 8/10 of a degree above absolute zero. And then we're using the Palomar 200-inch telescope, which is a very nice telescope. It was sort of a temple of 20th century astronomy. Many great discoveries in astronomy were made there. And it's a really, really fun place to work. It was the largest telescope in the world for probably about 50 years, from the 1930s to the 1990s. And it's still a very heavily used astronomical telescope. So anyway, we even coupling this giant telescope to this detector, we still only get 1 photon at a time. But we actually just received the first light from this Psyche spacecraft just a couple of weeks ago. So it's been a lot of fun. Let's see. There's also another kind of, once you know how to do free space optical communication, you can also do quantum communication, which is basically, if you remember those quantum computers that I was talking about? Well, it turns out that if you want to, say you have this information that's in this quantum system, if you want to distribute it from one place to another, it turns out that it's very hard to do that through like an optical fiber on Earth. The easiest way to do it is actually with a satellite. And so you would like in the future to be able to distribute this quantum information between different quantum computers by using this space-to-ground quantum communication, where you have individual photons which are prepared in special quantum states. And we made these fancy peacock-shaped detectors to do just that. I'm going to just mention one other application of our detectors. So we have a graduate student in our group, and she's doing her PhD research trying to use our detector technology to search for dark matter. Does anyone know what dark matter is? Okay, that's good. Actually, nobody knows what dark matter is. Turns out is a big problem. So dark matter is, but there is a few things that we do know. If dark matter is this very mysterious stuff that makes up most of the matter in the universe. So everything that we have in this room that you see, you are interacting with through the force of electromagnetism. So the light that you see here is electromagnetic. Your sense of touch is electromagnetic. You know, the nerves in your fingers are pushing against the table. Your sense of smell is electromagnetic. Your whole interaction with the world is electromagnetic. Now, what would happen if you had a particle that didn't feel the force of electromagnetism? It would be basically totally invisible. You would never know that it's there, unless maybe you had so much of it that that the force of gravity actually makes your planet move around a little bit, or something like that. So astronomers have realized that there are some serious discrepancies when they try to figure out how much stuff there is in the universe. So there's a couple different ways you could imagine trying to figure out how much stuff there is in the universe. If you look out at a galaxy with a telescope, you can look at the shape and the size of that galaxy, and you can say, okay, I can see my galaxy has, is such and such a shape and size. I know it's not flying apart, so I know it has to have a certain amount of matter in it in order for the gravity to make sense, for it to stay together in this particular shape. And you can also take a look at how much light is coming out of the galaxy, and you can estimate how many stars are in the galaxy, and you figure, okay, each star has so many number of planets, etc. And you can figure out how much material is in from looking at the amount of light. Now the problem is, those two numbers don't give you even remotely the same result. There is clearly way more stuff in the universe than you see when you look out at the light. And this is also well known by all kinds of other astronomical effects. If you look at the way that stars move around, people know quite clearly that there is a halo, this fuzzy halo of matter out there that seems to be invisible, that we just can't see, that doesn't seem to interact with light. And this is called dark matter. So you might ask yourself, well, all of the stuff in the universe, you go out to the desert, right, and you lay back and you look up at the stars and you think, oh my God, there's so many stars and so many planets and there's just so much stuff and I'm so small. Turns out, that's less than 5% of all of the stuff in the universe. If you add up the mass and the energy of the universe, all the elements on the periodic table, all the light, all the dust, all the gas, all the stars, it's actually less than 5% of all the material that's out there. So that's pretty humbling, I think. The rest of it, a little more than a quarter of it, is this stuff, dark matter. And most of it is the stuff we know even less about, called dark energy, which seems to be what is fueling the expansion of the universe. So we know very little about dark matter except that it has to be there. there's so many astronomical observations from the last 100 years. We know it has to be there, but what's it made out of? I mean, from a particle standpoint, no one has ever done an experiment where they said, aha, here's a particle of dark matter. And so people would like to build machines where they actually look for particles of dark matter. And so the way they do that is they write down the equations that describe, what would happen in an experiment if dark matter had this property or that property. And then you try to build a machine that would give you a different answer if dark matter had that property or not. And you try to wait and hope that a particle of dark matter moseys through your machine. So there are a couple of ways of doing that. One way is so what our student Jamie is working on is using a target of a semiconductor material of gallium arsenide. And when a particle of dark matter goes through that crystal, the thought is that, well, occasionally a little particle of dark matter could interact in some subtle way with one of the electrons in that crystal and produce a flash of light. And then you need a really nice detector to sense that flash of light. Your crystal has to be super, super cold anyway in order for this scheme to work. And so you might as well use a superconducting detector. And so she's been doing an experiment where she's been developing these very large area detectors and trying to couple them to these target crystals and trying to do different kinds of characterizations to sort of exclude the possibility that dark matter might be passing through them. There's also another experiment, don't worry too much about the details, but just looking for a totally different kind of dark matter, what's called axion dark matter, which is an experiment going on at Fermilab, which is a particle accelerator facility in Illinois. There, the theory is that the dark matter consists not of individual particles, but of giant waves that are like kilometers long, and that we just can't see them because it's very hard to make a machine that bobs up and down with a 1 kilometer wavelength, right? And so it turns out that if you, those hypothetical kilometer-long waves, which are called axions, if you put them in a very strong magnetic field, it turns out they can turn into real-world photons, according to the theory. And so this is an experiment where they have this funny-shaped mirror that looks here like this kind of funky triangular cylinder thing that will focus the light at all different wavelengths to one central spot if one of these axions happens to flow through this apparatus. And so these machines all need the very best, most sensitive detectors that you can possibly make. And those, of course, are superconducting detectors. And so we've been using them for that as well. Anyway, so that's all the technical stuff I have. Now I have a few slides about science as a career. Did anybody have any questions about like the technical part or anything? Yes?
So on I think on an earlier slide, when you were talking about the transmission of quantum data between the satellites, it said you couldn't measure the data from the computers.
Yeah.
And so I'm curious, how is it stored so that it's not measured?
Yeah. So this is a really tricky point. So the crazy thing about quantum information is that, like, a bit of data, you're storing information in some physical system. So it could be, is my pen pointed up or is my pen pointed down, right? I could make a data storage system where I have 1,000 pens, and I agree if I put, if the pens are sticking up, they're a 1. If the pen is sticking down, it's a 0. And I have my rack of 1,000 pens, I've stored a kilobyte of data, right? And each one, that's all there is to it. And you could make that any physical system. You could make it coins that are heads or tails, or little magnets on an old school hard drive, or pieces of silicon and a USB stick. Any physical system where it's just got 2 states, you can make a memory out of. Now, quantum information, on the other hand, is a super different animal. Quantum information has to do with the probability. If you were to like flip a coin, there's like a 50-50 chance it comes up heads and it comes up tails, right? Now, what if I told you that I want to store data in the probability that a coin would come up heads or would come up tails. Now, you won't know what the probability is unless you measure it like a whole bunch of times, right? So if you're storing information in a probability, turns out the quantum effects that you exploit have to do with the fact that the laws of probability turn out to be subtly different in quantum mechanics than they appear in the everyday world. And so the way to exploit that is to store your data as a probability itself. So if you measure it, you destroy that information because, it's no longer, it's no longer in this delicate, maybe heads, maybe tails state anymore. You've measured it, it's just heads, it's just tails, right? So that's why quantum information is insanely fragile and insanely hard to move from one place to another. So your options are basically, let's say you have an atom which is in this weird probabilistic state, and you want to get that. So you have two options. One option is you take it and you put it in some bottle that you try not to interact with in any way, shape, or form, and then you pick up that bottle and you carry it over to your other apparatus, and now you've transmitted your quantum information. That's one way to do it. Turns out that's not very practical for long distances. The other way is with a technique here where you do a certain set of operations on these two particles on each side, and you exploit a really wonderful, I don't really have time to get into all the details, but there's a really wonderful property in quantum mechanics of certain particles called entanglement, where you can have two particles that basically have a single identity. So if you have an entangled set of particles and you distribute them to the person over here with the one quantum system and the person over here with the other, you can do this sort of magic set of operations on them, and you can make it so the probabilities here basically disappear, get scrambled, and then that same probability appears over here in the other quantum system. And that trick is called quantum teleportation. And that is a way of distributing information between your quantum computer on this table and the quantum computer on that table. And believe it or not, that's what people want to do with this space-to-ground quantum communication, is to actually distribute an entangled state across two very different, distant points, like two sides of the United States, or the United States and Europe, or something like that. And for that, you need a satellite, and you need very good detectors, which is why we actually put the trouble through these peacock shape detectors. So, I don't know if that answered your question or just launched a bunch of new ones, but we can always talk more later. Anyone else have any technical questions? Or yeah?
In regards to the slide on dark matter and
Yeah.
the measurements, I was just curious, have you already done the theory for heat versus cold? Because you said you're using cold, but you're using the semiconductor, so I'm thinking that heat would be what you would want to see it.
Yeah, no, that's absolutely right. So people do both, actually, it turns out. So people can look for a signal of heat, like the dark matter particle comes and deposits a little bit of heat, and then, or you can use our detector to look for a flash of light, or in a perfect world, you would do both at the same time. Okay. And so there's actually very complementary experiments. So yeah, there are a number of groups that are using a different kind of superconducting detector, which is very sensitive to very small amounts of heat. So it turns out, just like the same way that light is quantized into photons, if you turn down the light, you get individual photons of light. Turns out heat and sound waves are also quantized in the same way. If you turn down heat enough, you get individual little particles of heat, basically, individual particles of sound, what are called phonons. And so you can have a different kind of superconducting detector that detects those phonons, the heat from the dark matter particle at the same time as this.
So for your study, you were using cold. What's the temperature you're looking at with the cold?
So this is done a little bit below 1 Kelvin, so about a little bit below 1 degree above absolute zero.
Okay. Thank you.
Yeah. Cool. Okay. Well, we have about 15 minutes left, so you folks are in high school, mostly, presumably, and almost. And so I just wanted to take a few minutes now to start talking about science as a career. And if you have any questions about that, I just wanted to highlight, first of all, that science is a super fun job. You get to think about really interesting stuff for a living. That's not something to take for granted as an adult. The fact that you can get up in the morning and think about really interesting stuff is really, really cool. And you keep getting to learn new things every day. You can keep reading new papers and so on and get paid for it. And people, you're always, every day I learn something new, and it's wonderful. And it's just a good way to move through the world. You get to play with lots of fun toys. You get to build cool machines. It's plug things in together in the lab. It's super fun. And it's a career where you have a lot of freedom to work on what interests you. If you have an idea to do some crazy kind of experiment, you can propose it, and if it makes enough sense for the government to fund it, you can do whatever you want. That's a really, really amazing thing in a career. Yes.
What new thing did you learn today?
Oh, I actually learned. There was a poster session at JPL today where different people who do different research present their different posters, and I learned about some really interesting materials that transmit light really well in the ultraviolet that I didn't know about. Yeah, and I would argue that knowing physics is just it's the ultimate superpower. If you just move through life knowing physics, the world is just better. If you look up at the sky and you know why the sky is blue, life is just good. And so you can have all of this if you have a career in science. So there's a process. Oh, my little arrows didn't show up at all. Sorry. But there's actually a fairly standard process for a career, at least in physics. And so it does take a certain amount of patience, but each step along the process is rewarding and fun. Generally, you start as an undergrad, as a physics major. That typically takes about 4 years. Then when you graduate, the standard path is to go to graduate school. And in the US, that takes typically about 5 years to get a PhD in physics. And graduate school is really all about research. So the undergrad degree, you take a lot of classes. You may start to do some research, but the PhD, that's really where you dive into one research project, and you really just love that project, and you do that project every day straight for 5 years, and then you come out and you're the world's expert on that particular project. Then typically, at the end of 5 years, you graduate, and you do what's called a postdoc, where you work almost like an apprentice scientist for a professor at a university or at a national lab like JPL. And that is typically 2 or 3 years. And then you can make the transition to like a full-time staff position. So that could be a position at a national lab like JPL or at a university or something like that. Each one of, just as a sort of a career note, each step when you go from each sort of block to block takes a certain amount of planning and a certain amount of practice. So you have to kind of think about, all the different kind of things that you might be thinking about already when you're thinking about choosing college to go to. Where do I want to live? What kind of lifestyle do I want to have, etc. One piece of good news is that while most people typically pay for undergrad, in physics at least, you don't pay for graduate school. So you get a stipend to live on, which is usually not extravagant, but it's enough to live on. Here in Southern, it's like $30,000, $40,000 a year in Southern California, but you don't have to pay. And then a postdoc, you get paid a little bit more. And then the hardest part is probably going from the postdoc to the full-time staff position, and that's there's a number of different options. And so this kind of gives you a sense. Oh, again, my arrows didn't show up, which is a little unfortunate. there's sort of a spectrum of different careers in science. So the three classic ones up here are to work in industry. There's lots of very fun, entertaining science jobs, especially things that skew more toward engineering, that you can do in industry. There's, crazy as it sounds, quantum computing companies out there and things like that, that there are places in industry where you can work on the kind of work that we do at JPL. There are national research labs like JPL, which are kind of in the middle, and then there's academia. This is the traditional being a physics professor at a university, etc. And industry, you tend to make a little bit more money, but academia, you tend to have more freedom. A national lab like JPL is kind of a nice, in my opinion, sweet spot, sort of in the middle, where you can get away with working on stuff that's a lot crazier than you can at just about any company. But at the end of the day, you still make stuff that people are relying on to work. And so in that sense, it's a little different from academia. Personally, I really like it. And then there's a whole constellation of other jobs which involve science, or that people with physics PhDs actually end up doing with their life. You can go into science policy, you can work in DC and help influence where the government wants to invest in science. You can be a K through 12 science teacher. I'm sure you all love your science teachers. That's another great career path. There's science journalism. Some people go and they work in finance, making quantitative models of how the stock market works and try to apply principles of physics to that. So there are all kinds of different things that you can do besides like the sort of classic choices of the sort of industry, academia, or a government path. So that's basically what I have. Thank you very much. I'm happy to chat with anyone that wants to. If you want to send me an email, I'm just mattshaw@jpl.nas.gov. And yeah, thanks so much for your attention.
So as Mr. Shaw said, I guess he'll be at the front to chat if any of you guys want to afterwards. For all the people who want to log their SNHS credits, they didn't give us a QR code this time, so there's just a sheet of paper up front you can sign your name on, and we will give that to the SNHS people to no log those. But yeah, that is all from me, so thank you all for coming.
Thank you.
Yes?
I have a question with the graduate